So, in the previous lecture we solved some problems covering topics in theory of probability. We will continue with that. We will discuss some problems related to theory of random processes. So, again there are a set of problems that I will be discussing in this lecture. They are not particularly ordered in any sequence of increasing complexity or any such scheme. They are just go by topics. So, we will now start with the first problem. The problem is as follows: consider the vector random variable y given by y1, y2, y3. It is a 3 cross 1 random vector. It is given that y is normal with mean vector mu and correlation matrix R given as shown here. Mean is 1, 2, 3 and correlation is matrix is this. We now form the random process x of t is y1 plus y2 t plus y3 t square. So, the problem is to find the mean, autocorrelations and cross correlations of x of t and x dot of t. Y is a 3 cross 1 vector. So, mean is 3 cross 1 and correlation matrix is 3 by 3, it is symmetric. Now, we define a vector n of t as 1 t t square. So, that x of t can be written as n transpose y. Thus, now expected value of x of t will be n transpose into expected value of y, which is 1 t t square and this is 1 2 3. This will be 1 2 t 3 t square. Now, we can differentiate the mean and get the mean of the derivative. In this particular case it will be b plus 2 c t, expected value of b plus 2 c t, which is 2 plus 60. Now, this matches with the derivative here 2 plus 60. So, that is fine as we expect. Now, the expected value of x of t1 into x transpose t2 will be n transpose t1 y y transpose n transpose t2. So, with that if we write now n transpose, this is 1 t1 t1 square transpose and this matrix y y transpose, and n t2 is 1 t2 t2 square. So, if we carry out this multiplication we get this expression for Rxx of t1 comma t2, and for t1 equal to t2 equal to t we get 4 minus 2 t plus 21 t square plus 19 t to the power of 4. So, now we have expected value as given here 1 plus 2 t plus 3 t square, and correlation function, autocorrelation function is as shown here, and from that I got the mean square value, and I can now get the variance as mean square value minus square of the mean. If I do that I get this expression and that I have shown here just to make sure that calculations are right. One check is that variance is positive, and it is to that extent the answers are reasonable. Now, this is the autocorrelation function for x of t. Now, if you want now cross correlation between x of t1 and x dot of t2, we can begin by differentiating this autocorrelation function and we get this expression minus 1 plus 9 t1 plus 12 t2 plus 38 t1 square t2. We could check this by directly evaluating expected value of x of t1 into x dot of t2. X of t1 is y1 plus y2 t1 plus y3 t1 square, x dot of t2 is y2 plus 2 y3 t2, and if we carry out this expectation operation we get what we got earlier by differentiating the autocorrelation function of the parent process. Similarly, we can find out now the autocorrelation of the derivative process by differentiating the autocorrelation function of x of t with respect to t1 and t2, and we get this function. So, this completes the solution to the problem. This helps you to manipulate simple properties of random processes, first and second order properties. In the next problem, we consider a random process x of t which is a into exponential j omega t minus theta. A is a deterministic constant, j is square root of minus 1 complex number, capital omega is a random variable with probability density function p omega of omega and characteristic function phi omega of lambda. Theta is a random variable that is independent of omega and distributed uniformly in minus pi to plus pi. So, we are asked to determine autocorrelation and power spectral density function of x of t and show that they have certain properties. Now, x of t is a into exponential j omega t minus theta, therefore, expected value of this is a is a constant. So, we get expected value of j omega t into expected value of j theta. Because omega and theta are independent, I can multiply these expectations. Since theta is uniformly distributed between minus pi and plus or 0 to 2 pi, e raised to minus j theta is cos theta minus j sin theta and averaged over 0 to 2 pi, that would be 0, therefore, the mean would be 0. Now, the expected value of x of t into x conjugate t minus lambda, x of t is a complex valued random process. So, when we find autocorrelation, we have to take the conjugation. If we do that, we get this to be a square into expected value of j omega lambda. This is nothing but, if you look at the expectation here, it is nothing but the characteristic function of random variable capital omega. So, that would mean Rxx of lambda is a square into characteristic function of lambda omega. Now, the Fourier transform of this, if we take, that is Sxx omega, will be the Fourier transform of this function, since this is the characteristic function of or proportional to the characteristic function of capital omega, the Fourier transform of this will be the probability density function. So, that is what we are asked to show, that autocorrelation function is proportional to the characteristic function of omega and power spectral density function is proportional to probability density function of omega. We will return to a similar problem slightly later and make some more observations on this solution. Another exercise in manipulating simple random processes, we define a random process y of t as x of t plus 2x t minus tau plus x of t minus 2 tau, where x of t is a 0 mean stationary random process with power spectral density function Sxx omega is c divided by omega square plus lambda square alpha square. The problem on hand is to determine the power spectral density function of y of t. So, we need to evaluate the mean and autocovariance of y of t and take the Fourier transform. We could do it in alternate ways, but this is what we are trying to do now. So, if y of t is x of t into 2 x t minus lambda plus x of t minus 2 lambda, the expected value of y would be 0 because x of t has 0 mean. Now, I can write an expression for y of t plus tau by replacing t by t plus tau and I get this expression. Now, if I multiply this with this and take expectation, we can show that we will get a somewhat long looking expression which involves, for instance, x of t into x of t plus tau is Rxx of tau, x of t into x of t into 2x t minus lambda plus tau is this, so on and so forth. So, we have to simplify this to get the required expression. Now, we have now determined the autocorrelation of y of t, which is the autocovariance also, since mean is 0. Now, we need to find the power spectral density function. Now, before we do that, we can quickly do a small calculation. If S of omega is the Fourier transform of R of tau, if you now consider Fourier transform of R of tau plus a, it will be R of tau plus a exponential e raised to minus omega tau d tau, and if I now substitute tau plus a as u, I will get this expression from which it follows that the Fourier transform of R of tau plus a will be exponential I omega a into SUU of omega. SUU of omega is the Fourier transform of R of tau. So, the time delay or a time shift in R of tau leads to a multiplier of the kind e raised to I omega a in the frequency domain. Now, using that, we can now write the expression for quantities like Rxx of tau minus lambda, tau plus lambda, etc. We can now take the Fourier transform and use the result that we just now obtained. We get the power spectral density function of y in terms of power spectral density of x along with these exponents and if we rearrange that and use the definition of exponential function e raised to I theta is cos theta plus I sin theta, we can show that the power spectral density function is given by this expression. A plot of this is shown here. The blue line is the power spectral density function of x of t, and this red line is the power spectral density of y of t. A similar exercise, here we consider two independent random processes x of t and y of t, which have 0 mean and are jointly stationary. They are independent, therefore, individual stationarity implies joint stationarity. Define a new process z of t, which is x of t into y of t minus lambda, where lambda is a deterministic constant. So, the problem is to find out the power spectral density function of z of t. Now, z of t is x of t into y of t minus lambda. So, expected value of z of t is expected value of this product, but since x of t and y of t are independent, I can multiply the expectations, and since x and y have 0 mean, the mean of z of t becomes 0. Now, I will construct the product z of t into z of t plus tau. So, that will be x of t into y of t minus lambda, x of t plus tau, y of t minus lambda plus tau. So, if we complete this calculation, we can show that the autocovariance of z of t is obtained as product of autocovariance of x of t and y of t. Now, we are asked to find the power spectral density function. So, a multiplication in time domain is a convolution in frequency domain. So, to obtain the power spectral density of z of t, we need to convolve the power spectral density function of x of t with power spectral density function of y of t. So, this is a required answer. A slightly different kind of problem. In next couple of problems, we will consider statically loaded beam structures where load is a random field evolving in space. That is the kind of problem that we will be considering. So, to start with, we will consider a simply supported beam of span L, which carries a distributed load f of x. The load is modeled as a segment of a stationary random process as f of x is equal to f naught into 1 plus epsilon xi of x, such that this xi of x has a 0 mean and it is a white noise with unit strength. So, we are asked to find the bending moment at the midspan and joint probability density function of reactions at the two supports. This is the problem on hand. So, we can begin by considering the reaction. This is the beam and this is the load. This is notionally shown. F of x is given to be a white noise. So, we cannot really the white noise is not physically realizable, but this is schematically shown here. So, we take moments of forces about point A, I get reaction B into L is f of x dx into x, that is the moment due to. So, we consider an elementary strip this, and this load is f of x dx. So, this is a moment. Now, from this I get R B as 1 by L x into f naught 1 plus epsilon psi of x dx, or in a slightly simplified form we get this. Now, you take the expectation, first term is deterministic, it stays as it is. The next one is f naught epsilon by L x into expected value of xi of x. Xi of x has 0 mean, therefore, the mean of the reaction is f naught L by 2. Now, I will consider the variable f R B minus f naught of L, which is another random variable, but now it will have 0 mean, and it is given by f naught epsilon divided by L into 0 to L x psi of x dx. The mean of this is 0. Now, if you find the mean square value, we have to square this. So, a single integral becomes double integral, and if we take expectation, we have inside this integral expected value of xi of x1 into xi of x2, which is given to be a white noise. Since psi of x is a white noise, this will be a Dirac delta function, and one of the integration can be done easily, and this is followed by the next integration. Because this is a simple function, I get the variance as this. So, what we have shown is reaction B is normally distributed with mean this and standard deviation this. Now, similarly, we can show the expression for reaction A. So, here we take moment about B and the expression will be this, and if we simplify and follow the steps that we have just now outlined for finding reaction B, we will find that mean of reaction A is again this number and standard deviation will be this. So, as you can expect, since structure is symmetric, loading is symmetric, the two reactions are identically distributed. Now, how about the correlation covariance of reaction A and reaction B? If you do that exercise, to do that exercise you have to take the expected value of RA minus mean of RA into RB into minus mean of RB. So, if you multiply this, each one is a single integral. So, the product will be a double integral and we get this, and we can now carry out integration with respect to x1 and x2. We again note that expected value of xi of x1 into xi of x2 is Dirac delta function. So, one integration can be done quickly, the other integration is also straightforward, we get this as the covariance. Since RA and RB are linear functions of xi of x, we are looking at quantities like integrals of Gaussian random processes. So, linear operation on Gaussian random processes preserves the Gaussian property, therefore, RA and RB will be Gaussian, and in fact they are jointly Gaussian, and this is a mean and this is a covariance function. Now, similarly we can find out the bending moment at the midspan, that is one of the part of our question. So, that is given by this expression, and we can manipulate this, and I have not filled up these details, I will leave it as an exercise to complete the calculation. So, first you find the mean and then find the subtract the mean from m and find the expected value of the square of that difference, you get the variance, and that is what you need to do by following the steps which you have done for finding reactions at A and B. Now, a similar problem, now we have a cantilever beam, it carries a randomly distributed load as shown here, Q of x is a randomly distributed load. The load Q of x is modeled as Q of x into Q naught 1 plus epsilon f of x. F of x has 0 mean, but expected value of f of x1 into f of x2 is not a function of x1 minus x2, therefore, the process is not stationary. This random field is not stationary. The question that is being asked is determine the bending moment at a section x measured from the free end. That means, what is the bending moment at this section? So, bending moment at that section can be easily found out. You find out the bending moment due to an incremental load q of psi into d psi, take moment about that section, we get this and then integrate from 0 to x. So, now you manipulate this expression, we get the bending expression for bending moment to be this. Now, mean of m of x is given by this. So, we are told that the expected value of f of psi is 0, therefore, the mean value will be q naught x square by 2. Now, I will deduct from m of x q naught x square by 2 as here and square it and take expected value. I get the variance of bending moment at x, and this is the expression that we have to deal with. Now, the autocovariance of f of psi is given to be of this form. Now, you can recognize that this has the form of a Gaussian probability density function. So, you can quickly see that we are writing expression for expected values of Gaussian quantities, therefore, evaluation can follow simple rules. So, following that, but the limits are from 0 to x, that has to be borne in mind. So, if we do this, there are various terms, we will get these 4 different terms. This is straightforward, you can check if these are right. Then we get the expression, if you simplify, variance of bending moment is given through this expression, where this capital psi of x is the Gaussian integral 1 by square root of 2 pi 0 to x e raised to minus x square by 2 dx. So, the applied load is a non-stationary random process, we are able to get the variance of the bending moment at any point x. So, the next problem is again on a cantilever beam. Here first go through the problem. A cantilever beam of span L carries a series of concentrated loads. The point of application of these loads are distributed as Poisson points on 0 to L. The magnitude of the loads are modeled as a sequence of IIDs with a common Rayleigh distribution with parameter sigma. So, we are asked to determine the characteristic function of the reaction at the support. So, what is happening is this W1, W2, W3, Wn are Poisson points, and reaction R and reaction M are to be determined. We are focusing on reaction R. Reaction R is nothing but summation of n equal to 1 to n of L Wn. This n of L is a Poisson random variable and Wn is a IID sequence of Rayleigh random variables. So, we are required to find the probability distribution of n. Now, what we are given is n of L is Poisson, therefore, probability of n of L equal to n is e raised to minus al, al to the power of n divided by n factorial, and W that is W1, W2, W2, W3 etc. form a IID sequence with a common density function Pw of W, and that is Rayleigh. We are asked to find characteristic function of R. So, what is characteristic function of R? It is expected value of I omega R, that is exponential of I omega n to 1 to capital N of L Wi. So, what we do is we condition on n of L, find a conditional expectation and then take the expectation on n of with respect to distribution of n of L. So, we begin by considering the situation when there are no loads on the structure. So, that is probability of n of L equal to 0 plus summation from k to 1 to infinity exponential I omega n to n from 1 to k Wi conditioned on n of L equal to k and probability of n of L equal to k. So, probability of n of L equal to k is given by this e raised to minus al to the power of k by k factorial, and this is nothing but the characteristic function of the IID sequence W. We need to multiply them because they are all independent. So, this becomes phi W of I omega to the power of k. So, we can rearrange these terms. There is a al to the power of k here and phi W I omega to the power of k. If we arrange these terms together, we can show that this characteristic function is nothing but exponential of al phi W of I omega minus 1. This phi W of I omega is a characteristic function of a Rayleigh random variable that we can show. I will leave it as an exercise. It involves slightly tedious integration. You can show that this is given by the characteristic function of a Rayleigh random variable by is given by this. So, you substitute that here and you got the solution to the problem that is posed. So, another simple example, the problem here is we are given a autocorrelation function beta exponential minus alpha modulus T2 minus T1 sin gamma T2 minus T1. Question is, can this be a valid autocovariance function of a zero mean random process? It is given that alpha, beta, gamma are all positive. If you recall, the required characteristics of a autocovariance function is it should be symmetric. So, this function is symmetric because if you exchange T1 and T2, the function remains unaltered, therefore, function is symmetric. So, it passes this test. Now, R of t comma t should be greater than 0. So, that if you see here, there will be a problem because sin gamma of 0 is 0. So, the variance becomes 0. So, since the function is not positive definite, the answer to this question is this cannot be a autocovariance function of a random process. Another example where you need to manipulate a random process and its derivative. So, consider x of t to be a stationary random process with 0 mean. We define y of t as x of t plus a of t into x dot t minus lambda, where lambda and a of t are deterministic. Determine the autocovariance of y of t. The autocovariance of x of t is given to be sigma square exponential minus alpha mod tau into 1 plus beta mod tau. So, this is a reasonably straightforward exercise which you need to do carefully. So, y of t is given as x of t plus a of t into x dot t minus lambda. Expected value of y of t is 0 because x of t has 0 mean. Therefore, derivative process will also have 0 mean. So, this is 0. So, the autocovariance is given by expected value of y of t into y of t plus tau. So, you need to write expression for y of t and for y of t plus tau and multiply all those terms, and if we carefully do that, the answer that we are looking for is r x x of tau plus a into t plus tau r x x dot tau minus lambda and so on and so forth. So, here the question is we need to evaluate r x x dot, r x dot x and r x dot x dot. We are given r x of tau. So, we need to use this formula to evaluate that. So, r x x of tau is sigma square exponential of this and into this multiplication factor. If you differentiate this, differential of modulus of tau leads to term called signum of tau, that needs to be handled, and then if you simplify you will get this as a first derivative. Now, this is nothing but r x x dot, we can get that quickly. Now, we can write signum of tau as u of tau minus u of minus tau and du by dt as Dirac delta function, and thus get the higher derivatives also, and go back and substitute into this expression, we will get the required autocovariance of y of t. Now, you please notice that r y y of t comma t plus tau, y of t is not stationary because this r y y t comma t plus tau is not a function of t alone, simply because there is a deterministic function a of t. Because of that, this y of t is non-stationary, but autocovariance is obtained as some kind of superposition of r x x of tau, each one of is a function of tau only, because x of t is stationary. Another simple problem: an undamped single degree of freedom system is set into free vibration by imparting random initial displacement and velocity. Characterize the system response. Determine the conditions under which the response can become stationary. So, this is a reasonably simple exercise. So, the problem is x double dot plus omega square x equal to 0, x of 0 is u, x dot of 0 is v, where u and v are random variables. So, x of t is a cos omega t plus b sin omega t. If you use the required specified initial conditions, I get x of t as u cos omega t plus v by omega sin omega t. Expected value of x of t is expected value of u into cos omega t plus expected value of v divided by omega into sin omega t. Since we are not yet given the information on expected value of u and v, this is the answer at this stage. Now, you find autocorrelation, you have to multiply u cos omega t plus v by omega sin omega t with x of t plus tau and carry out the calculations, and this is the answer that we get. But the question that we are asked is under what conditions on u and v the process can become stationary. So, now if you simplify this expression, if you look at autocorrelation of x of t, this is the expression here, and for x of t to be stationary, this r x x of t comma tau should be function of tau alone. So, for that to happen, in this expression, if expected value of u v is 0 and expected value of u square and v square by omega square are equal, we get autocorrelation to be function of time difference alone, but mean is still a function of time. So, we need to make mean equal to 0. See, mean is expected value of u into cos omega t plus this into sin omega t. So, the way that this can become time invariant is that expected value of u and expected value of v should be equal to 0. So, under this condition the process becomes wide sense stationary. Here we consider an input f of t which is 0 for t less than 0 and equal to e raised to minus 2t for t greater than or equal to 0 to a linear system. We have observed this output y of t is the output half e raised to minus 2t minus e raised to minus 4t. Given this information, the system is now excited by a Gaussian white noise excitation with unit strength. Determine the power spectral density function of the steady state response. So, notice that we are not given the governing differential equation here, but the input output relation in time domain is given. Now, f of t is exponential minus 2t u of t. So, the Fourier transform of this is you can quickly verify, it is 1 by 2 plus I omega. Y of t is given as half of e raised to minus 2t minus e raised to minus 4t into the step function. The Fourier transform of y of t can again be derived, and that is shown here, and based on this we can determine the complex frequency response function, which is ratio of y of omega to f of omega. So, if you do that, I get the h of omega is 1 by 4 plus I omega. Now, if the system is now driven by white noise, the output power spectral density function will be square of this transfer function into unit. So, the output power spectral density function is therefore this. Now, you can, to gain a bit of insight into this, if you consider the dynamical system x dot plus beta x equal to e raised to minus alpha t starting from rest, we can see that the solution to this problem will be in this form, and if we take now the 0 initial condition, we can get x of t is 1 by beta minus alpha this. That would mean that the given problem, the underlying dynamical system is simply x dot plus beta x is equal to some f of t. So, now on this system if you apply white noise, you can show that you will get the same transfer function that you got for this system is 1 plus beta plus I omega, and you can show that the power spectral density function would be similar to what we got by using other argument. In this example, we consider a non-Gaussian random process. So, here we are considering x of t to be f sin t plus phi plus y of t. Y is p is deterministic, this is p is deterministic, capital phi is a random variable distributed uniformly in 0 to 2 pi, and y of t is a 0 mean stationary Gaussian random process. We can also assume that y of t and phi are independent. Now, we are asked to determine the joint PDF of x of t and x dot of t. The question is, are x of t and x dot of t uncorrelated or independent? So, x of t is f sin t plus phi plus y of t. You take expected value, phi is uniformly distributed between 0 to 2 pi. So, expected value of this would be 0, the expected value of this also would be 0, therefore, expected value of x of t would be 0. Now, if you form the product x of t into x of t plus tau and take expectation, we get this expression where we have used the fact that phi and y are independent, and if you simplify this, we get this f square by 2 cos tau plus r y of tau. So, the process is the autocovariance function is a function of time difference. So, we can conclude that x of t is wide sense stationary. Now, how about the joint probability density function? So, you consider x of t to be f sin t plus phi plus y of t, x dot is f cos t plus phi plus y dot of t. First what we will do is we will find out the joint density function conditioned on phi. So, this will be p y dot y comma y dot, where y is x minus f sin t plus phi, y dot is x dot minus f cos t plus phi. We are finding conditional probability density function. Now, conditioned on phi, x of t is a Gaussian random process because y of t is Gaussian, and it will have now the mean which is x minus f sin t plus phi. So, if you mean will be f sin t plus phi. So, if you write this Gaussian density function, this will be the conditional density function. Now, the unconditional density function we have to carry out an integration with respect to the probability distribution of phi, that is as shown here. Now, if you make these substitutions, you can carry out this, you can show that p x of x dot, we can square this and take out terms which are free from psi and look at the terms which contain only this sin psi and cos psi. you can see that this integral is nothing but Bessel's function I naught, and this has this form, the first term, this is the second term. So, it is clear that x of t is a non-Gaussian random process, and if you look at the marginal density, again the same logic can be used. Probability density function of x conditioned on phi is this, and Px of x is the unconditional density function will involve another quadrature with respect to phi, and if you carry out this, again you will get answers in terms of Bessel's function. If you multiply the marginal densities, you can verify that you will not get the joint density function. So, from this what is the conclusions that we can draw? X of t and x dot of t are uncorrelated because they are stationary random processes, and x of t and x dot of t are not independent. So, it is an example of a non-Gaussian random process where process and its derivative are uncorrelated, but they are not independent. Now, while discussing random variables, we talked about what is known as Chebyshev inequality. Now, what happens to that inequality when we extend the logic to random processes? So, let x of t be a random process with mean mu x of t and variance sigma x square of t. Now, the inequality that we are asked to show is probability of modulus of x of t minus mu x greater than or equal to epsilon for some t in a to b is less than or equal to a quantity which involves the variance of x evaluated at a and b and an integral over a to b. Okay. So, this is a generalization of Chebyshev inequality, and this can be proven. I have indicated the steps. I would not like to go through this. You can take a look, they are reasonably straightforward. Now, let x of t be a stationary random process with 0 mean and autocovariance which has the form of a Gaussian probability density function. The question is, how many times can we differentiate this process? And we are asked to determine probability of x dot of t is less than or equal to 0.75 if it is given that the process is Gaussian and sigma is 1. Now, Rxx of tau is given to be this. From this, if I take the Fourier transform, I get the power spectral density function to be this. Now, if you consider the spectral moments, we can show that the since this exponent is decaying as minus omega square, all these integrals will exist for n equal to 1 to n etc., and spectral moments that 0, 2, 4, 6 etc. are nothing but autocovariance of the parent process and their derivatives evaluated at tau equal to 0, and since all these are finite, it follows that x of t is differentiable in the mean square sense to any order n. So, it is a fairly smooth process. Now, we can differentiate the autocovariance function and we can evaluate the various quantities at x equal to 0. So, Rxx of 0 is 1, from this it follows. So, if you differentiate this twice, you get Rxx dot, and if you put tau equal to 0, we get 1 by square root of 2 pi, and we can now write therefore Px dot of x dot is given by this, and from this we are asked to find out probability of x dot of t being less than or equal to 0.75, which is an integral minus infinity to 0.75, this quantity, this is given. So, the answer that we are looking for is this number 0.97. This is an interesting problem. Here we consider a random process n of t to be a Poisson random process with arrival rate lambda. Now, I define a new random process x of t which is minus 1 to the power of n of t. Now, we are asked to find the mean and covariance of x of t. X of t in the literature is known as semi-random telegraph signal. So, x of t, obviously n of t is an integer valued random process. So, whenever n of t is even, x of t will be 1, and n of t is odd, x of t will be minus 1. So, a sample will look like this depending on even odd combinations of n of t. So, x of t is minus 1 to the power of n of t. So, x of t is 1 if n of t equal to 0 or n of t is even, it is minus 1 if n of t is odd. So, what is probability that x of t equal to 1? It is nothing but probability of n of t is 0 or n of t is even, and that probability, since it is Poisson distributed, I can evaluate, and this I get to be that expression. And if you carefully look at this series inside the bracket, you recognize that this is cosine hyperbolic term. Now, how about the case where x of t is minus 1? We have to sum over odd integers, odd values of n, and if we do that, I get e raised to minus lambda t sin h lambda t. Therefore, the expected value of x of t would be, x of t takes only two values, with one probability is this, other probability is this. So, probability of x of t equal to 1 into 1 plus probability of x of t equal to minus 1 into minus 1. So, if we do that, we get the answer as 2 into e raised to minus 2 lambda t. So, this is the expected value of x of t. Now, what is correlation function, autocorrelation? Again, x of t takes two values, plus 1 minus 1. Therefore, the product x of t into x of t plus tau is 1 if there are even number of occurrences in t to t plus tau, otherwise it is minus 1. So, based on this argument, we can write the expectation of x of t into x of t plus tau, and we can show that the autocorrelation function is a function of modulus of tau. So, this process is wide sense stationary. That is, if I remove the mean, that is, if I define another process where x of t minus 2 e raised to minus lambda t, if I consider that process, that will have 0 mean and it is wide sense stationary. I will return to some comments on this example shortly. We will consider another problem. Here we consider a random walk that is performed on a 2-dimensional plane with a uniform step size of delta. At every step, the direction alpha I is a random variable, and alpha s are taken to be IID sequence with a common PDF that is uniformly distributed in 0 to 2 pi. Find the distribution of the x coordinate after n steps. That means, we start here, we draw a random variable to be distributed uniformly between 0 to 2 pi, and this is our realization. So, we take one step, then next this step, etc. So, after n steps, I am here and I am asking what is this x. So, x is nothing but I equal to 1 to n delta cos alpha I, where alpha I are the sequence of random variables that we have generated. So, what is the characteristic function of this? It is exponential, expected value of exponential I omega x, and that is this, and since alpha i's are all independent, I can get this, and we can evaluate this expected value of I omega delta cos alpha I, and given that alpha is uniformly distributed between 0 to 2 pi, I get this, and this integral is nothing but Bessel's function j naught. So, phi x of omega, which is a characteristic function of this random variable x, is actually the j naught of omega delta to the power of n. So, now we have to invert it to get the probability density function, and if we do this, we get this integral. This is the integral, and now if we do a series expansion for j naught to the power of n and consider the limit of n tending to infinity, number of steps going to infinity, such that delta of square root of n goes to c. That is a kind of limit that we used for taking a one-dimensional random walk to a Brownian motion process. In the same sense, this is done. If we do that, we can show that this process is this resulting random variable is Gaussian. So, this is an illustration of application of central limit theorem. So, you get the limiting density function to be Gaussian. If that n tending to infinity is not reached, the answer that we are looking for is given by this integral. So, another example which will help you to manipulate simple random processes. Let the time interval 0 to t be divided into a sequence of equal intervals of length t, that means I am considering some n t, consider a sequence of n Bernoulli trials, that means at every step probability of success is half. Now I define x of t equal to 1 if we observe success on nth trial, if it is minus 1 it is minus 1 if we observe a failure. So where t is between n minus 1 capital T into n t. So the problem is find mean and autocorrelation of x of t. There is a second bit to this problem where we define another random variable e which is distributed uniformly in 0 to capital T and independent of x of t. We define y of t as x of t minus e. So the problem is again determine the mean and autocorrelation of y of t. This is a fairly simple exercise that needs to be carefully done. So x of t is 1 if success on nth trial, x of t is minus 1 if failure on nth trial. So expected value of x of t is therefore 1 into half minus 1 into half, which is 0. The mean square value is again we can easily find out it is this. Now the product x of t1 into x of t2 is 1 if both t1 and t2 are contained in this interval n minus 1 capital T into to nt, otherwise it is 0. So that completes the solution to this problem. Now we introduce the this epsilon, that is the random variable epsilon. Now again we can find expected value and autocorrelation of y of t. We can first find the expected values conditioned on epsilon and then integrate with respect to distribution of epsilon. If we do that, we can show, I will leave this as an exercise, that the autocovariance of correlation of x of t in this case, that is y of t in this case, will be given by this function. So that is how it looks like here. It is a triangle over the step minus t to 2 steps minus t 0 to t and it is 0 elsewhere. Now this is a slightly question related to existence of random processes. So we are given a positive function s of omega and we are asked to find a stochastic process whose power spectral density is s of omega. Okay. Now there are two solutions. I will start with the second solution. What I will do is I will determine a square, which is area under s of omega, and define a function f of omega which is s of omega by a square. So clearly area under f of omega is 1 and it is positive 1. We assume that s of omega is equal to s of minus omega. So consequently what happens, f of omega is f of minus omega. So that would mean based on these two properties we can conclude that f of omega has the properties of a probability density function of a random variable. Now I define a random process x of t as a cos omega t plus phi, where omega and phi are random variables with omega having probability density function f of omega and phi is uniformly distributed between 0 to 2 pi and omega is independent of phi. So we consider now expected value of x of t, we can show that it is 0. You can start by you can find the mean conditioned on omega and then integrate with respect to omega. Conditioned on omega, this mean is 0, therefore the answer is 0. The autocorrelation function can be evaluated, this is reasonably straightforward, and you can show that the autocorrelation function is a square into f of omega, which is what we were expecting. That is autocorrelation is this, the power spectral density function is this, which is what we are expecting. Now interestingly, how does the samples of this function look like? They are, if you assume say this a is 1, they are all harmonics where frequency and phase are randomly distributed. But the power spectral density function can be specified by is a part of the specification of the problem. By that what I mean is, if power spectral density function is of the form say alpha square plus omega square, if I now assume that this is output of alpha x equal to psi of t, the power spectral density can be shown to be similar to this and the samples of this will look like this. But following the logic that we outlined here, x of t is a cos omega t plus phi, this also has the same power spectral density function. So, these two samples come from two different random processes whose power spectral density functions are the same. So, this would caution us to the fact that power spectral density function is an ensemble property. The two time histories that we see here represent samples from two different processes having the same mean and power spectral density function. Just to summarize, we saw that one example earlier x of t is minus 1 to the power of n of t, where samples were like square waves. So, in this if we deduct that mean, this quantity had power spectral density function or autocovariance function which is same as the power spectral density of this, the power spectral density of response of this system. But in this case the sample looks something like this. In the first case it is a square wave pulse, in this case it is harmonic. So, while interpreting power spectral density function in modeling, you have to take cognizance of this fact. At the end of the day it is a not a sample property, it is an ensemble property. So, this is what I am showing here. This is harmonic function, this is an erratic function and this is a square wave function. It is intuitively not clear if I say that these three samples come from three different processes having the same power spectral density function. Now, there are few properties of random processes with independent increments that I will take up in the following lecture, and that discussion will be followed by some problems on first passage time and extreme value distribution and so on and so forth. And then we will consider some discussions on the notion of say factor of safety and probability of failure. The notion of factor of safety essentially originates from deterministic outlook, whereas probability of failure when we talk about we are modeling uncertainties using theory of probability, random variables and random processes. So, how they are related? So, that is one of the questions. We will briefly consider the philosophical issue there, and then we will consider some more problems in response of dynamical systems to random excitations. Specifically, we will consider excitations which are non-Gaussian in nature and systems which are nonlinear, and we will apply in some problems the theory of Markov processes and derive the response moments, and all this we will consider in the following lecture. So, we will close the present lecture at this juncture.